Thank you very much, Hugh. I first met Otavio Bueno in England, where we were both doctoral students in philosophy. We were at different institutions, but we met repeatedly at a wonderful annual conference for young analytic philosophers. And immediately upon meeting him for the first time, I could tell that he was something akin to a philosophical Terminator. Relentless. Right? As I would head off to bed at a sensible hour, I would look over and see Otavio locked in debate with a sea of others. And then the next morning I would come down for breakfast and observe him in what seemed suspiciously like the exact same location, right? Victorious, surrounded by a sea of utterly exhausted and failing interlocutors. So fast forward this movie, some 20 years, and Otavio is now professor of philosophy and Cooper Senior Scholar in Arts and Sciences at the University of Miami. He's the chair of the Department of Philosophy and editor of one of the very top journals in analytic philosophy in the world, Synthèse. His work engages most centrally with issues in the philosophy of science, mathematics, logic, and through those lenses, relatedly, with metaphysics, epistemology, and art. He is quite possibly the hardest working man in show business. He is always, constantly traveling to the four corners of the globe to discuss his ideas. Otavio has authored or edited over a dozen books and literally hundreds of articles. In the spirit of applying mathematics, I actually did a little calculation of my own earlier today and worked out that in order for me to publish what Otavio will publish by a reasonable retirement age based on his current productivity, I will need to work until I'm 235 years old. But enough about him. We're all familiar with the phenomenon of using language to interact with the world. We learn languages growing up, natural languages, which involve associating certain sounds with certain concepts and using these sounds to describe the world and to communicate with one another about it. The use of language is an amazing and complex phenomenon, but we can all see, I think, in a basic way, how it comes about. We see things, we feel things, and we attach sounds to those things. But now imagine that you're able to develop a language that isn't necessarily about anything in particular. It's a purely formal language. Certain basic concepts are simply stipulated, right, and defined abstractly. And the consequences of these definitions are derived in a purely formal, logical manner. That's a lot of what we do in math. Mathematics can be thought of as a language, or different parts of math can be thought of as languages, each with their own syntax and possibly semantics. Now, imagine your surprise when you take this purely formal, abstract construction of yours and discover that it yields stunningly useful and apposite descriptions of concrete things in the world. Things for which, unlike a natural language, it wasn't developed necessarily to describe in the first place. If you think about this a little too much, which we as philosophers are wont to do, it can seem truly astounding that this sort of grubby physical world of ours should turn out to be so practicably describable in terms of these utterly abstract, formal, foreign languages that can be, and often are, developed in complete isolation from the physical world. What bridges these worlds of the abstract and the concrete? Well, sadly, there is no answer to that question. Oh, sorry, that isn't what it says here. It actually says, we had no plausible answer to that question, right? Until now. And with that, it gives me great pleasure to introduce Otavio Bueno to talk about his book with Stephen French, Applying Mathematics, Immersion, Inference, and Interpretation. Otavio.
Well, first of all, I would like to thank you for the opportunity of having this discussion here at Books and Books. I would like to thank the folks from Books and Books for running this series. I think it's very important to have that kind of interaction between the university and the community at large. And I would like also to thank my dearest friend, Anjan, for the lovely introduction. Of course, it's all down the hill from now on, right? This is a book that, it was funny, when Stephen and I start working about it, we thought, we're going to finish this, in 6 months, right? It took us almost 2 decades, right? And as we work through the details and the issues, there are other things to consider, complications, all the projects we got involved, until one day we said, look, that's been long enough, we need just to finish this, right? So we said, I went to the UK for a summer, I sat down, basically, he came first here, right, in Miami. I locked him in the hotel and told him, look, you need to finish this, and, otherwise I won't let you out, right? So we did a lot of progress there, and then over the following summer, he returned the favor and did the same thing when I visited him in the UK. And eventually we put the whole thing together. And the idea behind this book is we thought that there was a lot of mystifying ways in which mathematics is presented. Right? So first there is this conception that most people end up having about mathematics as this body of work where you have these solid truths that have been established once and for all. They never change. They, if true, are necessarily true. And the progress of mathematics is a process of adding up, piling up theorem after theorem, right? So what Euclid proved in the ancient Greeks, just part of the same thing that the latest result in a journal in mathematical analysis would just add you, right? And that's a kind of prevalent image that we have, I think, in large part because it's a very convenient picture. It makes mathematics look very neat, very tidy, very organized and clear. But also, it's a very misleading picture, right? And it makes mathematics very unhuman and very unhuman-like in all kinds of ways, right? We all know about the imperfections we have, false starts, things that went nowhere, and amazing returns, and we find all of that in mathematics. Right? But you need to look, and one of the things we try to do in the book is to look very carefully at the history of mathematics and mathematical practice. Right? So, and then it becomes very clear that the kind of monolithic picture that you have about mathematics is completely false. Right? And what emerges as a result is a very different picture of mathematics. Right? So, and in particular, so this is a book where we consider issues about the application of mathematics. Right? So, and there we also find kind of 2 extreme views. Right? So you have on the one hand this view that, isn't it amazing that a physicist needs to solve some problem, and all he or she had to do is to pick up a little piece of mathematics out of the bookshelf, and there it was, ready to be applied, and squeeze it into the world and perfectly tidy. Right? Yeah, it would be pretty amazing if that's what happened. Right? And then when you look at the actual process in which mathematics is applied, you'll find something very different and far more interesting going on. So I'll give you an example. So for example, when in 1989, Mark Steiner wrote a book called The Application of Mathematics as a Philosophical Problem. Right? And he tries to argue that there is this problem about how we can possibly make sense of how mathematics is applied to the world. After all, mathematics is all these abstract things, talking about numbers, functions, sets, things that are not in space and time. How can that stuff possibly connect to things in solid, changing, sort of elusive that we all experience in the actual world? right? And so when he gives an example, so he opens up a textbook in quantum mechanics, and then he says, "Oh, look, you look at the quantum mechanics, and one of the way that the theory is now formulated invokes something called Hilbert Spaces, right? The Hilbert Spaces are space of vectors. I don't know if you remember vectors. Sort of think about an error in a coordinate plane, right? And you have two errors, and you can join them and add them, multiply them. You can all do kinds of cool things with these little things, right? A Hilbert space is a space like that. Some properties that we don't have to worry about, but that's what it is, right? And then it turns out to be an extraordinarily useful device in order to formulate ideas from quantum mechanics, right? And then Steiner in his book says, isn't it amazing? You have this mathematics, theory of Hilbert space that David Hilbert, one of the greatest mathematicians of the 20th century, developed completely independently of anything about quantum mechanics. In fact, it was developed way before any quantum theory had ever been thought out. It turns out to be perfect. How can we explain that, right? And it looks very mysterious if you just look at the end product, right? Whatever you get in the textbook of quantum mechanics, because then it seems that the theory of Hilbert space was just literally taken out of a hat, right, and applied to physics. Now let's see what really happened, right? So if you go back to 1926, right, you had two different formulations of quantum theory, right? So there are physicists dealing about behavior of atoms, right, and their properties and electrons, and trying to figure out how to describe those things. And then come along Heisenberg with a theory, it's called matrix mechanics, and say, look, one way you can formulate this is in this purely algebraic way. We have these matrices, right, and in terms of them, you can calculate exactly the behavior of the quantum phenomena, right? But don't ask what's going on between measurements and things like that, because that's not a good question to ask, right? And you had, around the same time, a very different formulation that Schrödinger developed. It's called wave mechanics. That says, look, what's going on is they're physically real waves, right? And what the electron is this long wave that propagates through the world, right? Then there are issues with this interpretation. Maybe what he meant is just a probability wave rather than a physical wave bouncing around, right? But these couldn't be more diverse theories, right? One is a theory of discontinued phenomena, matrices, little points, right? The other is these wave-like things, continuous in space, right? It turns out that roughly either of these theories generate the right results, right? For example, about the predictions about the hydrogen atoms, out of these accounts. And physicists were puzzled. They said, well, how come? You have fundamentally different theories, basically telling getting it right as far as the observable phenomenon is concerned. How is that possible? Well, here's an easy answer. The theories are equivalent. That's why, right? So just different ways of saying the same thing. So, okay, it's not enough to say that. You need then to prove that they are equivalent, right? So Schrödinger in 1926 sits down to prove that result, right? Mind you, you have one space of wave mechanics is a continuous space, and you have the space of matrix mechanics, which is discontinuous, right? So he proved the easy side. How can I add the little discontinuous points into the continuous one, right? Oh, that you can do. Hard part is the other side, right? Because I have far more structure here than I can squeeze there. So footnote, Schrödinger in his paper. I haven't been able to show that, but more work is needed. The physics community at the time was so obsessed with trying to have that issue settled that they said, look, Schrödinger proved the equivalence, even though he acknowledged that he didn't, right? Then comes along Dirac, and Dirac is a quite interesting character, and he is someone who is very careful thinking about, okay, how can we massage the mathematics to get the results? So he creates something that it's called the delta function, which is a kind of weird name because it's not really a function, right? And he knows that it's not really a function, but it looks kind of like a function. And he tells a story about, okay, when it's okay to apply that function, right? And when it's not. And the trouble is you get some inconsistencies if you're not very careful with working with that function. So he tells a story when it's okay, when it's not, and prove the equivalence in that way, right? Of course, the equivalence had to be proved in a way that would violate standards requirements of consistency, because he's using a function that's not really consistent to get the result, right? So here's the situation. Attempts to prove the equivalence between the two formulations of the theory. One attempt just proved one side and didn't quite get the job done. Another attempt says, okay, I can prove it, but in a sort of inconsistent basis, right? And tell a story of why it's kind of okay, right? Right. Then 1931, John von Neumann comes along, and he looks at this mess. He's a mathematician, right? All these other people that I've been talking to so far are physicists, right? And physicists are more, let's put it, less concerned with fine details about careful mathematical formulation, right? They want to get the results done, and they're happy with that. A mathematician says, well, that's not good enough. We need a little more than that, right? So von Neumann, in a beautiful book called Mathematical Foundations of Quantum Mechanics, which actually I highly recommend, even if you know nothing about quantum mechanics, read the introduction of the book. It's actually very interesting. He lays out his understanding of the situation, right? And he says, look, here's the situation we are now. He basically tells the story that I just told you, right? And it would not have been the first time in the history of physics that we need to change our mathematics because of needs from the physics, right? And he's obviously thinking here about the infinitesimals, right? And when Newton and Descartes and Leibniz created the calculus, right? And they had to talk about magnitudes that are very small and changes that occur under extraordinarily small situations, right? But there are still magnitudes that are positive, even though it's smaller than any number. So those are the infinitesimals, right? And the trouble with those infinitesimals is that they're inconsistent. And you find derivations about that in the following way. You say, look, the infinitesimal is a number that is positive, right? So you can divide by it. So you divide. And at the end of the calculations, there is an infinitesimal left. And said, well, it's so small that you can treat it as zero, and you can ignore it. So it's not zero, and it's zero, right? So in the same derivation. So that made people absolutely, the mathematicians at the time, crazy about that. So look, I understand that you can formulate the calculus, and in fact, Leibniz and Newton got all the rules for the calculus exactly right, working on an inconsistent basis, right? If you go and study some calculus, the kind of derivation rules that you learn are exactly the ones that they came up with, right? To this day, I'm amazed, right, that they come up with that reasoning on the basis of a system that is inconsistent, right? And it's quite an achievement. So that's what von Neumann is referring to. So look, because they developed this theory, an inconsistent theory, or kind of inconsistent theory, so that they could use it in physics, so that they could use the calculus to do Newtonian mechanics, right? So von Neumann looks at that and says, well, okay, maybe the same thing needs to happen in the case of quantum mechanics. We also need then to revise our mathematics, swallow some inconsistencies, so we can then go ahead with the physics. However, von Neumann says this is not needed. Not in this case, right? And that's the insight that he has. And because he says, he looks at the mathematical spaces, right, of matrix mechanics and wave mechanics. And he says, obviously, these spaces are not isomorphic. That they cannot be equivalent to one another. One is discrete, the other is continuous, right? There's no way you can map those two things consistently, one into the other. However, and that's the insight that von Neumann has, if you consider the space of the functions defined on the matrix mechanic space, the functions defined on the wave mechanic space, the resulting space of functions are each a Hilbert space. And that's where the idea comes from. So we should start with the notion of a Hilbert space as the basic notion. And then he actually proves the equivalence between the two theories. But notice, he proves the mathematical equivalence of two Hilbert spaces. So his theorem is actually a mathematical theorem. And you say, but wait a minute, we're talking about physical theory. We're talking about waves, we're talking about matrices. Those are things about the world. Where are they in the von Neumann formulation? For him to prove the equivalence, he had to leave all of these things behind and basically chop out all of that, transform the physical theory into a piece of mathematics, and then prove a mathematical theorem about the equivalence between two Hilbert spaces. Right? So then it doesn't look like magic how Hilbert space came in. Right? They came in out of a very concrete foundational need of making sense of quantum mechanics in a way that is coherent. Right? And he did, von Neumann, right? In that way, but at a cost. Right? And the cost was sort of forgetting about the ontology, the physical ontology of the theories in question, right? What these theories were ultimately about. So again, we have here an intriguing dilemma, right? Because the story goes, well, so von Neumann proved an equivalence, right? And it's mathematically impeccable, the result that he proves. But it's not an equivalence about the physical theories, right? It's an equivalence about a mathematical framework used to formulate the physical theories. And that's different. Our book insists on the importance of drawing that distinction very carefully and very thoroughly. Because we think a lot of the discussions about the application of mathematics try to blur the distinction, right? So the physics and the mathematics are just kind of, they go along together as though it's just part of the same package. Whereas a careful attention to the way in which the mathematics is used in theorizing in physics and in economy and other areas suggests that we need to be very careful, separating, right? What is the mathematics? What is the interpretation of the mathematics, right? So the book has the subtitle, as Anjan said, Immersion, Inference, and Interpretation, right? The idea is the process of applying mathematics is ultimately a process of drawing inferences. Why do we care about using mathematics? So we can draw inferences about things we care about. The trouble is, the mathematics often allows us to explore connections in ways that way outstrip the physical phenomena that we are trying to deal with. So often there's more structure in the mathematics than in the physical world that we're trying to describe. So part of the game of making sense of the application of mathematics is how to make adjustments to the mathematics and to the physical phenomena so they can converse with one another. And it's not always that those adjustments work. Right? I'll give you an example of a case that doesn't seem that it worked. Right? So suppose you're interested in modeling consumer behavior. Right? You say, well, what do people have? Right? Well, they have their budget, right? And so they go to buy things in the market limited to how much money they have. That's the budget that they have. On the other hand, firms and companies have their profits that they're trying to make, right? And so there is some demand and there's some supply. And if you studied microeconomics, so you find this sort of beautiful little pieces of analysis where you have, this is the demand function, this is the supply function, and there is a point in which there is an equilibrium between the two, right? Here it is. I remember as an undergraduate, I was taking a class in macroeconomics, and I was puzzled, said, wait a minute, you have to prove that there is disequilibrium. You cannot just assert that that's the case. So I was sort of bugging the poor professor and said, well, how can we prove that? I said, well, then you have to go to the mathematics department, right? Because you need some analysis here to be able to prove those things. So I went there and never returned. So then I was completely taken by it. So this is really interesting, right? It's a completely different way of thinking about it. But what happened in the case of microeconomics was, once you have your phenomena, right? People buying things, companies selling them, and demands and supplies, and this all complicated interaction. So that's the phenomena we're trying to make sense. On the other hand, we have mathematical models. We have all these models of analysis that would allow us, look, I know how to calculate the maximum of a function and maximize it. So you're talking about maximizing your profit or maximizing your budget. Well, we can make very good sense of that in terms of the mathematics. So you immerse, you select some bits and pieces of the economic phenomena you're interested, you immerse that into the mathematics. And once you've done that, boy, then you have all the rich implications and derivations and inferences that you can draw out of the mathematics, right? Of course, you get a result, but that result is just about numbers, right? And then you need to interpret the result back in the world. And that's the interpretation. So immersion, how to map from the phenomena to the mathematics. Inference, how to draw the consequence once you have the mathematical model. And interpretation, how you read back from the results that the mathematics gives into the world. So the idea of the book is you can make sense of ways in which mathematics is used by exploring this framework, right? This inference, immersion, inference, and interpretation. So in the book we go over a variety of different case studies, primarily from the use of mathematics in quantum mechanics, but there are other examples along the way. They help make sense of the complexities and the difficulties involved in that process, right? Now, a lot of interesting things happen, right? Because once you have that framework in place, and you are then sensitive to the actual details of the way in which mathematics is used, you can start sort of dissipate some of the kind of rather mysterious ways in which the mathematics is presented when it's applied, right? So an example that people also often raise is with the discovery of the positron. Right? When people say things like that. Isn't it amazing that Dirac, just by considering a mathematical equation, uncovered a new particle in the universe? Sure, that would be pretty amazing, right? If that's what happened, right? Now, let's look at what exactly happened in that case. So, first, to have a sense of what's going on, if you remember that, when you're doing some even high school physics, so you have those equations of motion, right? So you have two cars, car A and car B are moving in opposite directions toward one another at the following speed, right? And that's the distance between them. How long it will take until they crash, right? That kind of, and these kinds of equations are second-order equations, so the solution often may involve some negative results. So you have positive and negative, and then the question is, what do we do with the negative results, right? And then you say, well, ignore them; they don't mean anything, right? There's no negative time, right? So, right there, you already have an interesting feature, right? The mathematics is providing more than the physical world requires. So, what do we do with that? We call that super, structure, right? So that extra structure. Sometimes the extra structure can be a distraction. Sometimes it can actually be very helpful. And the question is how to deal with it. Our analysis is what's crucial in those cases is to be very careful about how you interpret the mathematics. So the example of Dirac is an illustration of that. Because Dirac stumbled into an equation, which we now call Dirac equation. It's a differential equation, similar to the equation of the sort of the motion that I just mentioned. It's just that what counts as solutions of these equations, rather than numbers, are functions. Right? So you have, the details doesn't matter. So you have an equation, and that equation had negative energy solutions. So 1926, Dirac writes a paper. Hey, here's a cool equation. It accounts for these interesting things. By the way, it has these negative energy solutions. What do? Ignore them. Just like in classical mechanics, they don't mean anything. 1928, he comes back and says, all right, forget about that. Here's what's going on. These negative energy solutions stand for holes in the space-time. And so we are uncovering here some new physical structure. Right? And immediately, Heisenberg and File pointed out to Dirac, said, look, according to this whole theory, protons and electrons have the same mass. And that's just empirically wrong. So, okay, scratch that. 1930, Dirac is determined. He comes back, says, okay, forget about the holes. Here's what's really going on. There is a new particle that has exactly the same mass as the electron, but the opposite charge. And that's what those negative energy solutions stand for. Right? 1932, 2 years later, Anderson, an experimental physicist, messing up with his instruments, identified something that, with a lot of work, could be traced back to this new negative electron, positive electron, right? Which we now call positron. Right? People ask Anderson about this case, and he asked, did you know about Dirac's equation? And he said, yeah, I heard it, but I was very busy, working with my instruments here. That, as far as I'm concerned, and this is a literal quotation, the discovery of the positron was an accident. So it's a very different picture, right? Because what we have is the same piece of mathematics, Dirac equation, is compatible with three entirely different empirical outcomes. One in which it doesn't mean anything, one in which is empirically wrong, and one in which, with a lot of work, you can use to support some physical discovery. So the idea that Dirac simply stumbled into this and found a new particle out of the blue just by staring at a mathematical equation seems to be just a mystifying description of what the scientific discovery. Right? Of course, this looks far less exciting than it would be. And of course, physicists often like to just say things boldly, right? So that it will look deep or puzzling. So they like to say things, look, according to quantum mechanics, the same object can be in two different regions of space at the same time, right? Whoa, how is that possible, right? I wish I could do it. In fact, you can do it, as long as you are long enough. Right? Think about a road, right? That is in Miami, but it's also in Coral Gables, right? So, all right, but that's not so exciting, right? So, in many ways, the book is an attempt of bringing a fair bit of common sense, right, to discussions about the application of mathematics, right? Try to say, look, if you be sensitive to historical details, if you be sensitive to mathematical and scientific and physical practice, you realize that, just like anything else involving humans, there are things work not, in ways that sometimes they have to be adjusted, massaged, sometimes they fail, sometimes there's luck, and it's not sort of mysterious, right? At least we don't have to make them mysterious. And we learn quite something interesting, because then the picture that results about mathematics is one in which mathematics is a far more humane and human activity, right? Full of the false starts, holes, troubles, but also bold ideas, in the determination to find out what's going on, and interesting and worthwhile discoveries, right? So the book is a reflection on that, right? And also it covers other things about sort of why mathematics, despite being indispensable for our best theories in the world, need not be true, right? Why is that you can talk about things without believing that they exist? And you might be surprised. So, well, of course we do that all the time, right? We talk about Mickey Mouse and Sherlock Holmes. We don't believe that they exist, right? And but you'll be surprised how philosophers think, no, but if it's indispensable, the thing has to exist. right? And then part of the book is to try to disabuse that kind of picture and say, so when I sort of, like my colleagues in the physics department, so do you believe that there are vectors in a Hilbert space, right, out of quantum mechanics? And they look at me as though I just came from Mars and said, of course not, right? This is just a mathematics, right? And that kind of common sense response, I think, often gets lost in the ways that some philosophical control of the practice is are articulated. So in the book, we try to sort of resist those things. And hopefully offer a picture about mathematics and mathematical practice that is closer to home, right? And make it more amenable and hopefully more interesting as well. Thank you very much.
We have some time for questions.
Yes?
Are you in touch with the Santa Fe Institute?
Well, yes and no. I know some people there. I've interacted with some of them. Yes.
Okay, just curious.
Yeah. So, there are a lot. Look, just to be clear, I think mathematics is an extraordinarily interesting field, right? And we cannot possibly do science without mathematics, right? What we try just to resist is the mystification of the use of mathematics.
Well, there are artists and writers out in the Santa Fe Institute as well. It's necessarily math and physics.
Right. No, that's true. It's just that the way that often mathematics is presented, right, as though, look, you have all these discoveries, right, as though they came out of thin air, right, and they didn't. Yeah. So, and I think that kind of attention to the details is important, and otherwise, I think we get just the wrong picture about what mathematics is about. Of course, I'm talking about applied mathematics, but a similar story can be talked about pure mathematics, right, as well. I think on that, what I would recommend, I think the most beautiful book ever written on that was Lakatosh's Proofs and Refutations, right? So the book is a dialogue in this classroom of extraordinarily gifted students, right? And they're trying to settle a conjecture that Euler made up in the 17th century about the classification of polyhedron, right? In terms of the number of sides, faces, and edges. And there was a little equation that Euler put out there. And of course, Euler had this incredible mathematical intuition, and he said, well, this is true. He didn't even bother to prove it, right? He said, well, it works for this case, that's good enough, right? Proofs are for those mortals who don't quite see the truth of the result, right? And of course, it was a proof that eventually Poincaré, almost 200 years later, proved. And what the book does is sort of you have the give and take of the dialogue of trying to prove and then coming up with counterexamples. And people say, no, look, this is not quite right because here's a polyhedron that does not satisfy the equation. And then people say, whoa, that's not a polyhedron, that's a monster, right? To call this something else, clearly that's not what polyhedron is meant to be. And then you need to refine the concept of a polyhedron so that, okay, in a way, of course, that the original conjecture is not just a definition of what polyhedron is. So you need to, there's some give and take about how this process. And what Lakatos does is says, look, proofs do not prove. They refine naive conjectures. Right? So you have this naive conjecture, and it's this process of give and take, of trying to prove the result, facing counterexamples, analyzing the proof, adding some additional assumptions, getting some lemmas in, and then changing the concept as you go along, eventually until the thing is proved.
What was the name of the book again, please?
Proofs and Refutations.
Proofs and Refutations.
Yes. It's a beautiful book. And in the footnotes, Lakatos actually tell the actual story, right? What happened, who said what, how certain things were proved, and so on. And that's, I think, it's a reflection about mathematical practice, right? And I think he does capture very well the phenomenology of trying to prove a result that you don't know, right? Lakatos, Lakatos, right? And it was published by Cambridge University Press, and it's a lovely book, and it gives us this sense of again, why mathematics is not monolithic, right? But you need to look at the history. Of course, if you open a book on polyhedron, you just get the result there, and it looks like, all right, good, we're done, right? And that all the process of refinement of concept, revisions and reformulations are integral to mathematical activity, right? So in the book, we don't discuss pure mathematics as such, right? Occasionally, but it's primarily thinking about the application side. But a similar story can be told about pure mathematics. Yeah. Yes?
So do you think that math was invented or discovered?
Excellent. That's a very good question. So it's interesting because Stephen and I actually disagree on a number of things, right? And we find a common core of things that we agree, and we work on that, and we point out, in a way, people can add their own metaphysical assumptions to the picture that we offer, right? So the question you ask, to answer it depends on your views about mathematical ontology, right? So Platonists typically would say, look, mathematical objects are out there. It's our job to discover, like it is the job of the geographer to discover new lands, right, and the lay of the land. Nominally says not quite, right? So we make things up. So we're not discovering it. We are just introducing the concepts and then working through the connections among them and trying to refine the picture. So for them, it would not be a process of discovery, right, but of making things up, right? So we're inventing them, right? And so you ask my own view, right? I'm not a Platonist, right? So, but I think mathematics is objective, right? There are facts of the matter, even if objects are not out there. My actual view is I'm agnostic about the existence of these things, right? So, but if you have to pinpoint in terms of nominalism or Platonism, I'll be closer in heart to the nominalists, right? But the thought is the following. I don't think you need to settle that matter, right? Whether there are independently existing mathematical objects that we're trying to describe with our theories or not. I don't think that issue impacts mathematical practice at all, right? So, namely, you can understand the practice in ways that are completely independent as whether these objects exist or not, right? So you can run a little thought experiment. Right? Suppose that tomorrow, mathematical objects that used to exist no longer will, right? Would that make any change to anything, right? To bridges and skyscrapers and mathematicians proving results? I think the answer is no, because the existence of these objects, the independent existence of these objects, is not part of the practice. The practice goes just fine independently of that. So the argument I use is we don't need to settle that ontological question to make sense of the practice, right? That's an added on. So it's something that you can describe the practice by adding a layer of interpretation to it. Say a Platonist, for example, would say, oh, and by the way, these objects that we're talking about in mathematics, they exist independently of the descriptions. The nominalist would say, oh, by the way, these objects don't exist at all. I think these are all layers of interpretation that we don't need, right, to settle the matter. Having said that, so we introduce concepts. Of course we introduce, right? Mathematical concepts are things that we make up, right? Mathematicians do that. Once you have some concepts and you have principles relating those concepts and you have a logic, what follows from these concepts or not is not up to you. And in that sense, you get objectivity. So it's not that, oh, you can, say whatever you want, and that's fine. No, well, you can say whatever you want, but you may say false things, right? So once you introduce some mathematical principles and you have a logic in place, what follows from those principles is no longer up to you, right? On pain of inconsistency, right? And so in that sense, even if the objects don't exist, the objectivity of mathematics is secured, because it's not up to us what the results are.
What's an object?
Sorry?
What are you defining as object? I don't know what objects are.
Well,
this thing could
yeah, this is a physical object,
no,
right?
but that electron could be anywhere. I don't even know. An electron here from this object could be anywhere in the universe according to the mathematics. I mean, I don't know what an object is and isn't. I don't know where it stops. So when you say object, I mean, if I look at a sunflower, I can say that there's seeds here and there, and I can approximate what a seed is.
Right.
I can see a mathematical formula, something mathematical going on there. But you ask me what a sunflower is, I don't know. I can say, well, it's just right there. Is it really? Well, it's here too now.
Right. So good. So let's draw a distinction. One thing is a physical object, something that it's in space and time. So the flower is in space and time. So it's in front of you.
In all of space.
Sorry?
It could be in all of space and all of time. So I don't know what it is.
No. So for concreteness, we have this microphone, right? It's here, right? So it's
Electrons could be here.
well, but then it won't be in the microphone, right?
The probability is that they're there, but the probability that I
Not as long as when you measure it,
Yeah.
when you observe it, the wave function, that is what you talk about, will collapse on the value that you measure. So thinking in this way, actually you are breaking one of the postulates that are the base of quantum mechanics, that measurement is not a physical event as all the others, because indeed somehow you are making the wave function to collapse in the measurement you are doing. If you're measuring position, then you will see the electron in a given point. Then you repeat that measurement 100 times, and the percentage of where you find the electron will match the mathematical prediction, the probability that you say.
probability, but there is a probability.
But don't mix like intrinsic probability, that is the one of quantum mechanics, that it's different from statistical probability. Statistical probability is what we use when we don't have a full description of the system we are dealing with. But quantum mechanical probability is intrinsic. Actually, there is a really like nice exchange of letters between Einstein, who actually didn't believe in that, and all the other scientists we spoke about.
You're saying that the whole thing is probably right there.
But if I see it, it is there.
Yeah, that's right.
Because
So
observation changes the system I'm observing.
So then we don't know where it is.
Okay, so we need to draw a line, right, in the following respect. This is not a quantum mechanical object.
No,
This is a material object, a macroscopic one. Even though we would like to describe this in quantum mechanical terms, we have absolutely no idea how to do that.
Okay, you can magnify it without some magnifying glass.
Maybe we can move on.
I don't know what the boundaries of it are.
Yeah, so you have, the object may be vague, right? That is, I don't know exactly where it ends and where it, that doesn't mean that it's anywhere you want. It's not on the other side of the room, right? So the object is here. In any case, it's an object in space and time. When you're talking about functions, numbers, sets, they're not. They're not located in space and time, right? You may be, hit by a car, right? Hopefully, never will happen. But that doesn't mean you've been hit by the number one, right? So, and that's an important difference. And the mathematics offers a description about events in a mathematical framework, right? And that's separate from the physical world, right? And in part, that's the distinction that we draw in terms of one thing is the mathematics, the other thing is the interpretation of the mathematics, and you need to keep them apart. Often, by not carefully distinguishing them, we end up confusing things, confusing phenomena that are of very different kinds. And
Otavio, I'm really interested in the idea of immersion. So I understand, what happens afterwards. We make an inference and then we interpret. But could you tell us a little bit more about immersion? So one way I could imagine it is, we have some physical system or target that we're interested in, and we can immerse it in a bunch of math and see what sticks, right? And then there's some back and forth to adapt the math to describe that physical situation.
Right.
Sometimes we take the physical situation and we try to immerse it in some mathematics, and none of the things are sticking very well.
Right.
And so we actually need to develop some new math.
Right.
So are all of those things part of what you have in mind by immersion? What's going on in immersion?
Yes, good. Yeah, of course, the immersion is just the first step, right? And it is a selective process. You're going to select certain features of the phenomena that you're going to map into the mathematics, right? Certain features of the phenomena are going to be ignored. Right? Maybe the color doesn't matter, right? Or it maybe doesn't matter, how many of these things there are, right? It depends on the example, right? So you select those things and immerse it. You map them into the mathematical model, right? Now, as you said, sometimes we just don't have the mathematics to do that. Well, in the 17th century, people didn't have the calculus, right? So they need to do calculations with these tiny little variations. So they created one, right? And that's Newton and Leibniz instead, in order to calculate. In other cases, the phenomenon may be so damn complicated that we have no idea how even to create a mathematic for that. So think about an example that Mark Wilson gives, the mathematics of spilt milk, right? All right, describe that, right? So, and it's not the kind of thing that, given the nature of the phenomena, it's a minimal to any piece of mathematics. Not as though, we need just to find from the shelf, right? How to do that. So the process of adjustment there, of course, it's a process of identifying what are the salient features of the phenomena, identifying what piece of mathematics would be appropriate prima facie to deal with that. And of course, once you get the conclusions and the interpretation, you may realize that that's actually not quite right. So I mentioned early on the case of economics, right, the microeconomic model, because you have this idea, look, we can do all these maximization things once you immerse the behavior of the agents into the mathematics. And then you say, by the way, the rationality of the agents is given by the maximization, right? So they maximize, firms will maximize their profit, consumers their budget, right? And you can all calculate beautifully how that's done. Except that when you look back in the world, you don't find people doing that. No, to maximize your budget, you need to sit down and calculate every possible combination of each cent that you have, how you're going to spend, how much is going to go into food, and what kind of food, and what kind of rice you're going to get, right? Not to mention, everything else that you need, right? And so you basically have to spend all your time just calculating these little things so that you can find what is the maximum, the proper maximization way. No one does that, right? So the mathematics is in that sense misleading, right? So at least the idea that to be rational is to maximize your budget or that you have is just not empirically adequate, right? So Herbert Simon comes along and said, look, people don't do that. This is just a wrong description. What they do is they kind of do a satisficing, right? They say, look, this is good enough, right? Given the limited time I have to spend on searching for combinations of products and things, given that this is kind of the amount of money I'm willing to spend on this and sort of looks like a reasonable product, I'll go with that. Right? So, and he won the Nobel Prize in economics by doing that. But it comes with a price, because it doesn't have the neat mathematics to then do the calculations, and he has to do some song and dance as a result. So that's an example, right? So you can immerse because you do have just a very neat piece of mathematics that will give you interesting results, but some of the results, when interpreted, might be empirically inadequate. So then you may go back and say, well, maybe we need to readjust, right? And find, so in order to get something that is a little more empirically adequate, we need to change the mathematical framework.
I have time for one more quick question, then we can do any informal discussion after.
All right, yes?
How would you, in terms of interpretation, would you say that because traditional physics and traditional mathematics have the same underpinning sort of logical axioms, would you say that mathematical phenomena could support nearly any physical phenomena given that you map, correctly certain variables or occurrences?
Yeah, so what happens is typically the mathematics will have far more structure, more possibilities than what's actually can be realized in the physical world. So a famous example, if you have the axiom of choice, right? If you have a sphere, you can slice that sphere in finitely many slices, reassemble those slices into two spheres of exactly the same volume as the original one. Oh, how can you do that? Well, if you have the axiom of choice, you can. Now, don't try to replicate that at home with an orange. Right? You're going to fail because there are physical constraints about the slicing that would never satisfy the conditions for the slicing in the axiom of choice. Right? So what will happen is there are possibilities that the mathematics entertains because there are no physical constraints. And as a result, there are more things happening in the mathematics than can possibly happen in the physical world. So the trick is to identify how adequate, what is the adequate piece of mathematics, how it can be properly interpreted so that then you can get proper results. And sometimes you have to be lucky, right? And it also happens quite a bit in the development of mathematics, right? Or in science for that matter, right? So when we have when Newton, the discovery of Neptune is an example like that, right? Neptune was unknown at the time in the 18th century, and so they knew all the planets up to Uranus. And they noticed that the orbit of the planet didn't quite fit what Newtonian physics said it would. So Leverrier was so committed to Newtonian physics being right, he says, well, here's what's going on. There's a new planet, right, that's actually interfering with the orbit of Uranus. So at the time, they had no telescopes to find the thing. They had no idea where to look. So they used a law which is called Bode's law, right? So it's a sequence of numbers that tells what the average distance in astronomical units for each planet to the sun, right? So there is a number for Mars, the Earth, Venus, and so on. So they said, oh, what will be the next term in that sequence? And let's look there, right? So they did that. So they looked there. Of course, they had to develop better telescopes and so on. And eventually they found way off what Bode's law predicted. So the law that was used in order to find Neptune actually violated and refuted the very law, right? And many years later, when historians started looking at the calculations that Leverrier did about the size of the planet and so on, the calculations were full of mistakes. Despite that, you found the planet, right? So sometimes, you have to be lucky, right? And so be it. Despite that, of course, this is considered one of the greatest discoveries ever made in the history of physics, right? I love it, right? Because it's completely fortuitous, right? Everything was wrong, and it worked nonetheless. I think it's a nice picture. It's a good way to end as well. Thank you.
One last note, the book is on sale, and Otavio, I'm sure, will be happy to sign it if you buy a copy and bring it to him. And thanks to all of you for coming out tonight.
Thank you. Thanks for the discussion. So it should